In talking about induction, we're talking about creating a electrical charge in a conductor, and that's caused by a magnetic field causing electrons in that conductor to shift from one end to the other. So obviously, if the electrons move from this end towards me, then there's going to be more electrons on my end of this conductor, which makes it negative compared to this. So that would make this a voltage. There'd be a voltage across this, that difference in charge. More electrons here. This would be the positive end. This would be the negative end. So when I say that voltage is induced in this conductor, what causes those electrons to move? And that's the magnetic field. So if I have a magnet here and a magnet here, north and south, and those lines of magnetic field, those lines of magnetic flux are going across, and I take this conductor and I cut those lines, that's what causes those electrons to move. Now, if I just had the conductor sitting in a magnetic field, it doesn't cause any motion of the electrons. I have to actually cut those lines of flux. It's that relative motion between the conductor and the lines of flux that causes the electrons to move, inducing a voltage. So when you hear about induction, that's what we're talking about. A couple things about that. The faster that I move this, the faster that I cut the electrons, the greater the voltage that's induced in this conductor. So that's why this is a principle, basic principle of generators. The faster a generator turns, inside of there you have conductors moving around inside of magnetic fields, and we'll look a little bit more at that. But the faster generator turns, the higher the voltage output, because I'm cutting those lines of flux faster. So the speed that you're cutting the flux affects the magnitude of the voltage. Also, the direction of the cutting determines the polarity. So in the example that I gave, and I was moving down through this magnetic field, these lines of flux, my electrons were moving from your end to my end, making my end more negative than your end, which was more positive. But if I were to move upward from bottom to top, the opposite happens, and electrons move from my end to your end, and now your end is negative and my end is positive. Okay, we're going to start today's lecture talking about magnets and magnetism. And the reason that we're doing that is because magnets and electricity have a lot in common. In fact, you can make electricity with magnets, and you can make magnets with electricity. So we're going to talk about those principles and those applications for a little while. Here I'm looking at taking a piece of magnetic material. This is usually ferrous material or an iron-based material. And if I wrap conductors around this, like I've done here with this coil, and I run DC current through that coil, that creates a magnetic field around those conductors, as we talked about previously. And the magnetic field goes into this magnetic material, and the magnetic material can retain that magnetism caused by this this process. Now, if I want to demagnetize that piece of metal, I would hook it up to AC current, where it's alternating going plus and minus. So the direction of the current is reversing and essentially demagnetizes the previous magnetization process. So retaining magnetism. Here I have a temporary magnet, an electromagnet, and I have soft iron. And in this particular case, if I close the switch, the current flows through this coil, through this conductor, causing magnetic fields to develop around the conductor, and that magnetic field goes into this core, this piece of iron, causing it to be magnetized. So now this piece of iron becomes an electromagnet. Now, if I open the switch, the magnetic field goes away, and this particular type of iron is not the type that will keep that magnetism. So the magnetic field goes away. Now there's always a little bit of residual magnetism. So if I had an electromagnet like this, and let's say I take a screwdriver. I take a screwdriver and I wrap coil of wire, insulated wire, around the shaft of the screwdriver, hook those wires each end to a battery. Now the screwdriver shaft is magnetic, and maybe I put it close to some iron filings and it'll pick up a bunch of iron filings or paper clips or nails. Now that I take one end of the battery loose from this coil, that magnetic field goes away, and whatever it was holding, paper clips or iron filings, drops to the surface below. But maybe a little bit of iron filing stayed there. Maybe one paper clip stayed there, because there's always a little bit of residual magnetism. Now, the amount of residual magnetism depends on the material. And if I want this to stay magnetic for a long time, then I'll use a material that retains that property. And that's how that's how we make most magnets. There is such a thing as a natural magnet, but it's called lodestone. It's not really that strong. So most of the magnets that you see that are permanent magnets, we've made through this process with the appropriate types of metal. Basically, hard steel compared to soft iron. Magnetic poles you should be familiar with. You know that there's a north and a south. Just like the polarity of electrical field has positive, negative, the polarity of magnetic fields have north and south. You can see here, if this were placed on a piece of paper with iron filings, that's what these black things, these are attracted to the lines of force, the magnetic field. Those are those invisible lines of force or lines of flux that's created in a magnetic field. Notice that when we talk about the flux density, we're talking about how close these lines are together. And the strength of an electromagnet or electromagnetic field is determined by that flux density. So we can see that the flux density, or how close those lines are together, is really tight here. It's very dense, and so the magnet's always strongest at the poles. And here there are magnetic forces in play, but you can see that those lines are spaced out. So the center of the magnet is weak. So it's going to be the weakest right in the middle and strongest at the ends. The law of magnetic poles, you've played with magnets enough to know how this works. Here you have similar forces, and again, like electrical forces, similar forces will repel. And the opposite is true with unlike poles or unlike forces. Also important in looking at the strength of magnetic fields is the distance between the poles. As we get closer, the lines become more compact, so the density increases. That means that the strength of that magnetic field is stronger. If we pull the magnet apart, that pulls these lines apart so they're not as dense, and since magnetic field strength has to do with the density, the flux density of these lines, the magnetic field decreases with increasing length. Shielding. I will tell you a little bit about electromagnetic fields and electromagnetic radiation. So when we talk about electromagnetic radiation, we're talking about an electromagnetic field that's radiating out from its source. And of course, the magnet would have a electromagnetic field, but a lot of things create electromagnetic fields. Sunspots, radio and TV waves, rotating machinery. There's a lot of sources of electromagnetic radiation, and if those lines of magnetic flux coming from those various sources get into conductors, it can induce a voltage. And the conductor can be stationary. In fact, this is what happens with an antenna. The antenna is a conductor that's stationary. The radio station sends out its signal as electromagnetic waves. Those waves or lines of flux cut across that stationary conductor, the antenna. That induces a voltage in that antenna, and that becomes your signal, and that voltage is sent to the rest of the radio and processed through tuning and filtering and volume and things like that, and ultimately goes to a speaker to where you can hear it. So sometimes we want to keep that from happening. In a radio, in an antenna, obviously that's the intent, but in some cases we don't. We see here that if I have a piece of paper and a magnet and something that can be influenced by a magnetic field, the paper does nothing to shield this from this. Now here's an example where I would like to have some shielding, because here I have a sensitive meter. Maybe this is measuring something very small, like the heartbeat of a flea or something. So it's very sensitive. That means that it operates on a very little signal. Very little voltage will drive this meter. So electromagnetic radiation that's coming from sunspots or radio stations or TVs or wherever, if it gets into this meter, the wires and conductors in this meter, that can cause noise, cause interference, cause the signal to be inaccurate. It can cause this the induced voltage to mix with the voltage from the measuring device that this thing's looking at and give you faulty readings. So here I can't use paper, as we saw before. It doesn't provide shielding, so I'm using metal. I've got an iron ring that surrounds my meter, so any electromagnetic fields or radiation coming from any source heads towards my meter, but gets in this metal and travels along it and exits the other side. Because magnetic flux, as we'll see here in a little bit, it likes to travel through ferrous materials, and it's a lot easier for that to happen than to flow through air. So coming in here and given a choice of traveling through metal or traveling into air, the magnetic lines of flux travel through the metal. Uses for permanent magnets. So whether we make a magnet out of lodestone, which is rare, or whether we make one out of a hard iron bar or a piece of iron, how do we use those? Here's an example where we use it in a deflection meter. I've got a permanent magnet here, okay, and I have an electromagnet here. And if I were to run current into this, then I have this electric magnet. And the more current that I run through here, the stronger the magnetic field is. So I have a permanent magnet and I have an electromagnet. And when you have two magnets close together, they'll either be attracted or repelled. And so that's what happens. This creates a magnetic field that tries to get this to move. And since it's pinned in the middle, it can rotate. So the magnetic force will cause this to rotate and this meter will deflect. So basically, the more current you put in here, the stronger the magnetic field, the further it will move. So I use this to measure electricity. Maybe I use it just as an amp meter, or maybe I use it using another device called a transducer that takes some physical phenomenon and converts it into electricity. An example of a good transducer would be a microphone. A microphone takes sound waves and converts it into electrical signals, and I could see the loudness of a sound by running the microphone into this to these two leads right here and cause this to deflect. Here is a permanent magnet generator. I've got north and south, and so that means there's lines of flux that's crossing through here, and now I have conductors, and if I cut those lines of flux with these conductors, that induces a voltage in the conductors, and one side becomes more positive than the other. If I hook a load, then current will flow. This one's hand operated crank. Here's a permanent magnet motor, and just like the meter that we talked about before, here I have permanent magnets, and here I have conductors. And when I run current through these conductors, that causes this to become magnetized. Now this is an electromagnet, and again, I've got a magnet here and magnets out here. This side may be being pushed, this side's being pulled, and because it's able to rotate, it will. So motors, and we'll talk more about motors and generators in another learning module, but motors operate because of the interaction of two magnets. The magnets that are in the poles on the outside and the magnets that are in the armature or the rotor on the inside. A loudspeaker is another example. I said in a radio, you've got a conductor over here. The waves come in, induces a voltage in that conductor. And so there's my signal. But the thing is, there's a lot of other stations in there besides the one I want to listen to. So there's where you get into tuning or filtering another circuit downstream from the antenna. So I'm going to filter out all the ones that I don't want, plus any noise that came from sunspots or ignition systems in cars or whatever. Filter all of that out and be left only with the particular radio station I want to hear. The signal's not loud enough to cause enough current to drive this speaker. So I have to have an amplifier as well to boost that signal up. And we'll talk more about amplifiers in another learning module too. But what will happen is I have, again, like a motor, I have a permanent magnet here, but inside I have an electromagnet, and that signal coming from my radio goes into that electromagnet, and I get motion. And the electromagnet's hooked to this cone, so as this electromagnet moves back and forth in response to the signal, so does this piece of membrane, paper or plastic, and when it moves back and forth, it pushes air back and forth, which is what sound waves are. And if in the case of a microphone, that's where it all began. We took sound waves, air moving back and forth, converted it to electricity, amplified it, maybe tuned it a little bit, and then shot it to a speaker to get turned back into air moving back and forth. Here I'm using a magnet switch. Maybe you've got this shows this being on a window, and here's my switch, and this is wired up to an alarm system. And as long as this is closed, we'll say, as long as this is closed, my alarm is off. But for some reason this were to open up, then that would set my alarm off. So this magnet is attached to the window, and if I move the window up, the magnetic field will go away from this switch, and the switch will change states, and that will cause the alarm to sound. This is showing the magnetic field that does develop around a conductor. Whenever I have current flowing through a conductor, that magnetic field, those lines of magnetic flux, develop around the conductor. The stronger the current, then the more expansive, the further out these lines will expand. Here's another view of it, looking in and then looking from this side into it, and then looking back this way. Probably one thing to point out here is current flows through there and these lines of flux develop. And again, like I say, the stronger this current going in, the larger these rings will become. These will start to spread out with increasing current. But notice that the top part of the wire, the top half of the wire is different magnetic field. So the top and the bottom are north and south. Here's the showing if I take that conductor and coil it, the resultant parallel lines of flux that are created around this create this net result. A simple electromagnet with just an air core. In other words, the center has only air. It's still an electromagnet. Here's an electromagnet with probably iron, which is going to make that magnetic field go into this metal, and this metal will become highly magnetic. If I run the current in this direction, then this is north and this is south. However, if I reverse the current flow, then the opposite thing occurs. Factors that determine the strength of an electromagnet. Well, we already said the more current that you have, the stronger the magnetic field, but also the type of core that's in the center. Because if there's nothing here, it's just an air core, yeah, there's a magnetic field, but once you put some sort of ferrous material, iron or steel, in here, that tends to collect those lines of flux from around these coils and get concentrated in the metal itself. So it becomes a very strong electromagnet. And also the number of turns and the spacing. So the tighter that I make these and the more turns that I have, then I'm going to have a stronger electromagnet. Comparing current and flux. The magnetic flux traveling in metal is very similar to electrons flowing in conductors. And here I have current going through an electric circuit, and here I have magnetic lines of flux traveling around a piece of iron. Comparing resistance and reluctance. As we talked about the shielding, we said that the lines of flux like to travel through iron, but not so much through air. So reluctance is to magnetic lines of flux as resistance is to current. So in electrical resistance, you see the current is impeded by that resistance. And in a magnetic circuit, the reluctance affects how much flux will flow. How do we use electromagnets? Well, here's a good example, a lifting magnet. So I've got this huge coil in soft steel, which is going to make a temporary electromagnet. Temporary one because it's soft steel. And there's my coil, and this thing's hooked to the end of a crane. And I've got a cable going down to it so I can energize that coil and make it magnetic. So I put this over a bunch of scrap iron, or I'm loading containers off of a ship. I can lower this thing down, throw the switch, the current goes through the coil, magnetizes it, and now I can pick up my load with this. And I position to where I want to let go, open the switch up, the current stops flowing, the magnetic field collapses around the coil, becomes demagnetized, and things fall off. Remember I said that there's some residual magnetism, so if I was picking up scrap steel, maybe there's still some nails or pieces of scrap that's still attached. If I pick up a cargo container, it just lets go of the whole thing. Here I'm using an electromagnet in a generator. We showed a generator before that had a permanent magnet, but if I have an electromagnet for my field coils like I have here, I can vary the output of this. Besides varying the speed, to change the output of a generator, I can vary how strong this magnetic field is, because the stronger this magnetic field is, the higher the voltage that's going to be induced in these conductors as they turn around. So this gives me an adjustable generator output without changing the speed of it. A solenoid, we use these in our trainer. We've got a coil inside of this, and when we run current through that, it causes the plunger to be pulled, or if maybe it's being repelled. But in any event, the magnet causes this plunger to move. This plunger may be attached to a valve that I can open valves like your fuel injectors is a good example of a solenoid operated valve. I could use it to operate switch contacts, and we would call that a relay. Those would be examples of solenoids. Transformers are an important component in electrical applications, and we'll learn more about it in a subsequent learning module. But notice here, what I've got is I've got a voltage of 120 volts coming into one of the circuits of a transformer, the primary circuit or the primary coil. So here's a coil of wire, and transformers have a primary circuit or coil and a secondary coil and circuit. Notice that the voltage is 120 volts on this side, but it's only 12 volts on this side. This is called a step down transformer because we're going from 120 down to 12 by a factor of 10. There's nothing connecting these two coils. The primary coil and the secondary coil are not connected. I've got a core here. I'll say they're not connected electrically, but they are connected magnetically. So let's see how this works. What's going on here? Okay, I'm running current into this coil. That causes magnetic lines of flux to develop, and those lines of flux are going to travel around in this magnetic circuit. Now, as it's traveling around this coil, now I've got cutting action, relative motion between a coil and lines of flux. The coil's stationary. It's not like when I was holding a conductor and running it through lines of flux. Here, the coil is stationary and the lines of flux are moving, but that motion is enough to induce a voltage here. Okay, let's take a look at this circuit. We see we have current leaving the battery, and as long as the push button is pushed down, current can go through it, continues on, lands on a screw terminal on this vibrating bell device, circles around this electromagnet, continues on through this set of contacts, down this conductor to this screw terminal of the device, and then to complete the loop returns to the battery. So there's a complete circuit here, and whenever that current flows and energizes these coils, this electromagnet that's formed will pull this piece of iron towards it, and because it's pivoted down here, and as that pulls, the hammer hits the bell, ding. But also, when it flies over here to hit the bell, this set of contacts breaks. It's like a switch. The contacts break, the current stops, these coils de-energize, and the hammer falls back this direction. But once it does, it reestablishes the connection, the contacts close again, and current begins to flow again. This becomes magnetized again, and again the bell
is hit by the hammer. So this back and forth action causes that vibrating bell circuit that you're familiar with. Now here's another look at transformers, perhaps a little deeper of a look. We see that we have a primary coil here and a secondary coil here. Notice the difference in the number of windings. This is a big factor with transformers. The ratio of windings, number of windings in the primary compared to the number of windings in the secondary, determine if it's a step up or step down transformer, and by how much, what the multiplier is in terms of step up or step down. We can see that happening here. We have a primary coil. Primary coil is fixed, but we see as this changes, as we increase the number of windings on the secondary voltage goes up. If this number, or when this number and this number are the same, then whatever goes in on the primary, it's the same voltage coming out. We can see that when the greater number is on the secondary side, so is the greater voltage. And when there's a smaller number than the primary, then the voltage is smaller than the primary, and that would mean it would be a step-down transformer. Some more illustrations that kind of show what's going on with the flux, with the current, in terms of primary and secondary. All right, so we'll talk a little bit about batteries. There's different variations shown here. Okay, in a voltaic cell, the principle is that you have more electrons on one side than you do the other, and that difference in charge is what creates that electrical tension, what we call voltage, that force. And the way that it works is you have a copper electrode, you have a zinc electrode. They're chemically different, atomically different because of their atomic makeup. And when they're immersed or submerged in electrolyte, that causes a transfer of electrons. So what you see are the electrons are leaving the copper electrode and moving towards the zinc electrode. So both electrodes become ionized in opposite directions. And if there's a path for those electrons to move completely around, as shown here with this light bulb as a load, the current will flow and operate the bulb. A single cell is 1.5 volts. So here is a single cell battery. It's a D battery, it's 1.5 volts. And this is the schematic symbol for it. Here I've got a 9-volt battery. So that means that there's 6 cells in a 9-volt battery. The amp hour rating is an important feature along with the actual voltage. The amp hour rating, which is amps times hours, tells us how long a battery can deliver current to its load if we know what the current demand of that load is. In this particular case, the amp hour, it's 2 amps times 8 hours, so that's 16 amp hours. A carbon zinc battery, cutaway diagram, the same kind of principle. You have 2 different metals. You've got this terminal here. This is a carbon positive electrode. And then your zinc negative comes down to the bottom here for the negative. And you've got an electrolyte that facilitates that transfer of electrons to where, again, you get a difference in charge, greater number of electrons at the minus terminal than you have at the positive terminal. Connecting batteries together, you see that a series connection of cells, got 12 in series with other 12s, and it would be shown like this in a schematic diagram. Notice that you have a negative terminal, and then you connect the positive to the negative, just like this. And they're additive, just like resistors in series are additive. Here, I have a voltage that is the sum of these. And my amp hours are unaffected. These are examples of where batteries are in series, and I put this in here because when you look at them, they look like they're parallel because they're side by side like two parallel lines. But the fact of the matter is, if you would really look at the electrical connections in these, you'll see that it's negative hooked to positive because these are hooked together right here. So you've got this terminal that's positive, and current would flow this way and out the negative of that one. Parallel connections. Here I'm showing you hook negative to negative and positive to positive, and schematically it would look like this. And your amp hours are additive in a case like this. This is a jump start situation where you're going to hook your batteries in parallel, positive to positive and negative to negative, using, in this case, the ground of the engine ground, a metal component or a metal strap, whatever is used for the ground. An example how to do that. Well, maybe not. So, batteries wired in series. You see here I have a 6 volt, a 6 volt, but I've got 12. Again, I have the same number of amp hours, but when I hook them in parallel, so here the voltage increases, the amp hours stay the same. Here the voltage stays the same, but the amp hours increase. Testing a battery under load. If there's no load on the battery, you just measure it as it's sitting there out of its device, you'll see that the voltage is higher than its rating. But whenever you put it under a load, you'll see that the voltage will drop down. This is normal. This is a normal way that a battery works, and the reason that it does that is because there's an internal resistance inside the battery. Because of that internal resistance, as you see here, whatever this voltage is, when it's no load, when this load's not connected, we read a voltage here, and that entire voltage is across just the internal resistance. But now that I've put another load in series, the total voltage is divided among this resistance and this resistance. Now, obviously, you design a battery so that this resistance is much smaller than this, so that most of the drop is happening right here. Calculating the internal resistance, if you want to, you would do something like this. You would put an amp meter on it. You read the no load voltage, and then you put the amp meter on it and get the current. And so you use Ohm's law to say R is equal to V over I, and now you know what the resistance of that battery is. This would be useful to determine if you were unsure what kind of battery to use in an application, but you knew the resistance of the load. So you'd like to have a pretty big number, like 100 to 1. You want the load to be 100 times greater than the internal resistance, so the majority of the voltage will drop across the load when it's in series with the internal resistance. a lead acid battery, kind of showing the same components. You've got a couple different leads, an electrolyte, and there's a transfer and ionization that occurs that creates the difference in charge. Was going to read the voltage. The discharging action is when the electrons are moving away from the negative terminal, returning. But then if I'm going to charge it, here we're using an alternator, I'm going to charge it back, then the reverse direction occurs. The electrons are going back into the negative electrode. Here we're looking at measuring the voltage and the current as we're charging. We don't want to over voltage or under voltage, nor do we want to over current. Okay, now we're going to take a quick look at circuit protection devices. And it says here that circuits can be damaged or destroyed if we exceed the voltage and current levels for which they're designed. So fuses and circuit breakers are one of the most common and widely used protection devices, and you see different types of examples here. So here's an overloaded circuit. This is a branch circuit coming off the breaker box going into a room. It's rated for 15 amps, 120 volts, so we have 1500 watts. Now, I've got this sound system, which looks pretty old, and it's rated at 360 watts. Since it's 120 volt, we know it's plugged into 120 volts, and it's rated to consume 360 watts. We know that it's 3 amps that it's drawing, because V times I is the power. So there's 3 amps, we have 15. Now I plug this lamp in, it's a 120 watt bulb, and since we know that it's 120 volts, as all of these are, because they're all wired in parallel to a 120 volt source, then I've got 1 amp flowing here. Now I've got this space heater, 1440 watts, 120 volts. This thing's drawing 12 amps. And we know that heaters like this, electric heaters, draw a lot of current. So now I've got 12, 13, 16 amps, right? 16 amps. This would be enough right here to have tripped this breaker. And with these other things on it too, the 1 amp being drawn by this light, 5 amps being drawn by a 600 watt, like a heat lamp or something. So you can't turn all of these on at one time. In fact, depending on what you turn on at the same time, there's several combinations that would cause this to trip. So the solution is to find another circuit to plug some of these things on. The solution is not to put a bigger breaker in here. Why is that? Because this wiring that's been run was designed for 15 amps. And if I put a breaker in here that will handle 20 amps and the wire will only handle 15 before it starts to heat up, melt the insulation, start a fire, then we have a problem. A short between line wires, this will trip a breaker, because if my resistance is 0, which is the resistance of a short circuit, the current just shoots up towards infinity. So yeah, if I have shorted wires. From a schematic, it looks something like this, although this is being shown as a DC source, and this is AC over here. But I couldn't edit this picture, so I had to leave it alone. But a short circuit essentially goes from one side to the other, from one side to the other, one side to the other, and the current that flows in this loop without any resistance in it is so high that it takes out safety devices right away. A short between two circuits. You may have seen something like this. Let's see what's happened. I have a circuit here, and this happens, it's an automotive battery, it looks like, and it happens in automobiles frequently enough. But I have a circuit here, and if I have a switch, a fuse and a switch, and I'm able to turn on, ideally I would turn on this light with this switch. Here's the circuit as it's designed. Here's another switch, and it's designed to turn on this lamp. But if this wire and this wire are running together side by side, and which that happens in a car, and maybe this is going out to a trailer, or going to your taillights on the bed of a truck. Anyway, these wires run together. Over time, they may have come loose and are rubbing, vibrating against each other, maybe vibrating against a part of the chassis. And the insulation wears off, and the conductors inside eventually touch. Now I've got this circuit and this circuit touching. And so when current leaves this, when this switch is down, not only does current go this way to this light as it always has, but now, because there's another path here, it can turn this light on. So your brake light and your turn signal light, or your parking light, can both be on at the same time, even though you're not pressing the brake switch. It can still come on when this other switch comes on because of this type of short. Here's some examples of different kinds of fuses. Over here is the schematic symbol for a fuse. You probably have seen most of these. Some of them are very tiny. Some of them can be very large. Here's some circuit breakers, schematic symbol here. Some of these can be rather small, and some of those, this is out of a transfer station, power company, substation. And this out of a motor control center probably for a pretty big motor. This is a pretty big breaker here. Of course, they have current ratings that are indicated. The plug fuse, get a little diagram here to show you how it kind of works. The threaded side, you got a tip and a threaded side, like a light bulb. In one end of the connection, the current goes in here, circles around, goes through this fuse link, and then ends up touching the threaded part. So current enters the center and goes out on the threaded part. And as long as the current level is within the design of this, everything's fine. But if the current exceeds this, what this wire can handle, it will burn in two and break continuity in the circuit. It acts like an open switch. It works by melting in two. Here are other examples. You see the fuse link. They snap into these holders, and current enters this side, goes through the link, and exits back into the circuit. Got a link here. Here's a knife blade cartridge that goes in fuse disconnects, snap in, and this substance right here is a retardant. So when this thing opens up under high voltage, it doesn't draw a big arc as this opens up. This material tends to squelch that. Time delay fuses. In some cases, particularly when you're starting up a motor, there's such an inrush current. When the motor's first starting up, it takes more current at first than it does when it's up and running. So if I have a fuse that blows under that current, it would just blow immediately. A time delay gives the fuse time. It won't blow immediately. It has to be hot for a long time, and this solder will melt, and the spring will pull the fuse link away. So a big surge is not going to be enough, but a continuous surge over a short period of time will be enough to melt this and cause this to open up. Here's another type. This is a cartridge type instead of a screw-in type. Same thing happens. Um, this melts and the spring pulls things apart. Here's a renewable cartridge fuse. Some fuses, you can replace the links in them. This usually found in industrial situations. And you would just screw the ends off of this thing and pull this out, unscrew the link, put in a new link, screw it back together again, put it back into the circuit. Using an ohmmeter to test fuses. What's the resistance of a fuse when it's good? Well, it should be 0 because it's a short circuit, or very, very near 0 resistance. But if it blows and now it's an open circuit, well, then you should read infinite resistance. So, testing a fuse while it's in place. I guess first thing we'll do here is we look at the normal voltage. We're checking our meter and see incoming. Here's the incoming power, the line side, and this is the load side. So it's coming in on the line. We checked with the meter and we see it's 230 volts. Now we check on the other side and we see that it's 230 volts. That means that this point is getting to this point. This point is getting to this point, which means inside of here I have continuity. That means the fuse is good. But if a fuse is bad, something's happened here, because now I have 230 on my line, but I've got nothing on my load. Now the question is, are both of these bad, or one of them bad? Would I read anything different like this either way? And the answer is, I don't know. If testing it like this, at least one of these are bad. And for both of them to blow is kind of unlikely that they would both blow at the exact same time. It's possible, but I don't know. But here's how I can find out. I can take this lead off and put it up here, and if it goes from 0 to 230, then I know that this point's getting to this point, and I know that this fuse is bad. Again, if I take this point off and put it up here, and it reads 230, then I know this fuse is bad. And if I don't, then I need to check the other way. So I'll take this one and move it up here and see if it goes to 230. And if it does, then I know this one's bad. And if it doesn't, and I've already done this, then I know that both of them are bad. I can also measure across the fuse because, as we talked about, a short circuit, let's assume both of these fuses are good. I'm reading 230 volts when I read like this. I read 230 volts when I read like this. But if I were to take this lead and move it up here, what would I read? 0, because this point is the same as this point. If that fuse is good, it's a short circuit. The difference between this point and this point would be 0. The same thing if I looked at the difference between this point and this point. If the fuse is good, it should be 0. But if I look and I see that the difference from this point to this point is 230, then I know this is an open circuit and that the max voltage is across that open circuit. I've got all the pushing on this side and no push on the other. The difference between all push, 230, and 0 push is 230. This is important this is why we've talked in the past about what's the voltage across an open circuit, what's the voltage across a short circuit, why is it like that? Understanding that really helps in troubleshooting this type of a situation, which you will encounter a lot of times. When things aren't working down here, when this load doesn't work, one of the first things you look at is right here. Circuit breaker connection. This just shows that this is in series with my following downstream parallel branches. Notice that the circuit breaker is matched to the wire ampacity, the ability to carry current. The way the circuit breaker works is similar to a fuse, except what we're using here is a bimetallic strip. In a fuse, you've got something that melts, either solder or a link, and then once it melts, it's not renewable. You have to throw it away. A circuit breaker is better in that sense that you can reset it. And let's see how it works. A bimetal strip is one of the key parts of it. We talked about how different elements had different coefficients of resistivity, and one of them we talked about was coefficient of expansion. And we said that if you heat up one metal, it might expand so many centimeters, but a different metal may expand much more or much less, that they expand differently. And that's the principle behind this. I've taken two metals that have different coefficients of expansion, and as the current goes through them, it's going to heat up from friction, current running through things, and that's fine unless it becomes excessive. And if that happens, the heat is so much that this thing will start to expand. But the fact that one of them is expanding more than the other causes it essentially to curl. So a bimetallic strip will curl when it becomes overheated. And when it curls, it's going to come away from this and let these contacts be pulled open by this spring. This bimetallic strip is used in baseboard thermostats. It's used in twinkle lights, what makes the lights, Christmas lights, twinkle on and off. So it's a common heat sensing device. Thermal overload. Because motors draw a lot of current as they start up, you need time delay fuses and fuses that have to withstand a normal amount of current and also withstand that inrush current. So what protects a motor then from overcurrent situations. We know that the fuse isn't going to protect it because it has to be able to handle that inrush current. And that inrush current's temporary and doesn't harm the motor, but excessive current can harm the motor. So we need a way to protect the motor from overcurrent and the heat that's created, and we can't do it with a fuse because it's designed well over the damaging current that can occur here. So what we use is a sensing device in the motor itself, and it probably works along the same lines as the bimetal strips. As it heats, it causes a deflection and an opening of contacts. They're called thermal overloads. They open when they carry enough current that they heat up to the extent that creates the opening. And finally, lightning rod installation. So the lightning rods aren't designed to conduct a lightning strike away, because the fact of the matter is this wire would not withstand the current that would be generated by a lightning strike. But the way that it does work is that if you have a cloud that's ionizing, in other words, it's starting to charge up, and it gets charged up to a certain point to where that difference in charge creates such a high voltage that current flows through the air, through the high resistance of air as a lightning strike. To keep that from happening, we're going to take those ions as they're accumulating and discharge them from the beginning. So any charge that's accumulating in this crowd, we're dissipating or directing it away, draining it out before it can build up to the extent that a lightning strike occurs.